Humanity's farthest-reaching emissaries, Voyager Twin Probes, have been hurtling through the infinite void of space for more than 45 years. But now, a mystery of unprecedented proportions has unfolded in the dark heart of space, a discovery so baffling that defies our fundamental understanding of the universe. But what did it discover, and what secrets lie hidden within the data? In this gripping exploration, we'll unveil the shocking revelations as Voyager 1 has made an impossible discovery after 45 years in space. History of the Voyager Probes. Decades ago, a pivotal moment in history unfolded when two incredible spacecraft embarked on an epic journey into the cosmos, heralding the dawn of the space exploration era. The year was 1965 when Gary Flandreau, a brilliant mind at NASA's Jet Propulsion Laboratory, faced an enormous challenge. His mission is to chart the optimal course for a space probe to reach the distant gas giants within our solar system: Jupiter, Saturn, Uranus, and Neptune. Armed with nothing but a simple pencil, Flandreau made a groundbreaking discovery. He realized that in the late 1970s and early 1980s, these four colossal planets would align in a celestial dance of cosmic rarity. This alignment, similar to the stars aligning for a celestial waltz, held an extraordinary opportunity. A spacecraft passing by each of these planets could harness the invisible but potent force of their gravitational pull, accelerating like a speeding comet. Flandreau's calculations unveiled an astonishing possibility that what was once envisioned as a daunting 30-year odyssey from Earth to Neptune could now be accomplished in a mere 12 years, all thanks to these celestial gravity assists. But there was a catch, a significant one. This planetary alignment occurred once in a staggering 176 years. NASA, not about to let this extraordinary opportunity slip through their fingers, swiftly launched two identical spacecraft, Voyager 1 and Voyager 2, in the summer of 1977. Their mission was clear: to seize the full advantage of this rare cosmic alignment. Little did they know that these cosmic siblings would shatter records and redefine the landscape of space exploration. The luncheon missions of the Voyagers. On that historic September 5, 1977, the world held its collective breath as Voyager 1 embarked on a groundbreaking odyssey launched into the cosmos from Cape Canaveral, Florida. It was a daring venture, propelled skyward by the powerful Titan IIIe or Centaur rocket. A mere 15 days later, on August 20, 1977, Voyager 2 joined its cosmic sibling in this extraordinary journey, initiating a parallel mission of exploration beyond our wildest dreams. Their initial mission was to venture to the gas giants of our solar system, Jupiter and Saturn, and the enigmatic moons that danced around them. But these intrepid travelers had grander destinies in mind. They soon found themselves on an epic trajectory to the farthest fringes of our celestial neighborhood, charting the cosmic seas like celestial mariners. As the years passed, Voyager 1 and Voyager 2 achieved extraordinary milestones. They've endured the rigors of space and time, far outlasting any other spacecraft in the annals of history. Their unwavering dedication to exploration has taken them further from Earth than any human-made objects in existence. In a feat that forever etched their names into the annals of space exploration, they crossed the threshold into interstellar space, venturing beyond the sun's sphere of influence and into the uncharted expanse of our galaxy. More than 12 billion miles from Earth, these pioneering interstellar probes continue to defy expectations and surprise physicists with their invaluable data. Yet their most recent revelation has left scientists awestruck, an impossible discovery that defies explanation. We'll delve deeper into this mind-bending revelation shortly. The achievements of these Voyager twins are nothing short of awe-inspiring. Their early observations of Jupiter and Saturn's moons, conducted over 4 decades ago, shattered long-held assumptions. Previously thought to be lifeless, heavily cratered wastelands similar to our own moon, these moons were unveiled as geological hotbeds, teeming with active, complex processes. Voyager 2, in particular, blazed a trail of cosmic milestones. It became the first spacecraft to venture by Uranus in 1986, and a mere 3 years later, it executed a flyby of Neptune, cementing their legacy as cosmic pioneers of the highest order. To this day, Voyager 1 holds the distinction of being the sole spacecraft to venture along such a unique trajectory. While these cosmic pioneers continue their awe-inspiring odyssey, NASA has devised a clever strategy to prolong their operational lives. Over the past 4 years, they've opted to deactivate non-essential components and heaters, a conservation tactic that promises to extend their mission well into the next decade. With an anticipated mission end date of 2030, these indomitable explorers show no signs of slowing down. For the devoted scientists and engineers who have been part of this exceptional journey since its inception, this phase marks a bittersweet juncture. Their unwavering dedication and tireless efforts have carried the Voyager missions far beyond their original expectations. The Voyager Twin Probes' new discoveries. Meanwhile, the data brought back by the Voyager spacecraft has been nothing short of a cosmic treasure trove. It's not an overstatement to say that it has provided invaluable insights, fueling numerous scientific discoveries and igniting the imagination of countless researchers and space enthusiasts. Voyager 1 and Voyager 2 weren't just your run-of-the-mill spacecraft. They were meticulously engineered to be incredibly stable platforms, with a rotation rate over 15 times slower than the hour hand on a clock. This design ensured that as they hurtled through space, the images and data they captured remained exceptionally sharp, minimizing any visual blur. Their image-capturing prowess started to amaze scientists and the public long before their close encounters with the outer planets. Voyager 1, still months away from Jupiter, began transmitting images of the gas giant. These early visuals showcased the mesmerizing swirls of Jupiter's clouds and the iconic Great Red Spot, leaving NASA's Jet Propulsion Laboratory and the world in awe. Yet the most remarkable discovery was still on the horizon. It was the revelation of active volcanoes on Io, one of Jupiter's moons, that set the stage for the Voyager mission's groundbreaking observations. Io, slightly larger than Earth's moon, emerged as the most volcanically active body in our solar system. The spacecraft's instruments picked up curious signals from Io, and their vivid images confirmed the shocking truth. They unveiled towering volcanic plumes and a surface marred by the ejection of molten material. One of the most dramatic celestial spectacles recorded in the Voyager missions was the eruption of Pele, one of Io's most prominent volcanoes. Its explosive activity surpassed any volcanic eruptions on Earth, soaring an astonishing 30 times higher than the peak of Mount Everest. The fiery plumes it expelled covered an area nearly the size of France, leaving a lasting impression of the intensity of geological forces on this otherworldly moon. The Voyager spacecraft delivered a visual feast of over 33,000 images, offering a mesmerizing glimpse into the intricate beauty of Jupiter and its diverse family of moons. These images showcase the planet's vibrant bands of clouds and the astonishing variety of moonscapes in the Jovian system, each a unique world with its own story to tell. Long before the recent mind-bending discovery, the twin Voyagers were on a roll, amassing a treasure trove of scientific revelations. Among the most astonishing was the revelation of Jupiter's ethereal rings. While faint compared to Saturn's resplendent rings, their existence added another layer of mystique to the gas giant, defying previous assumptions about its celestial jewelry. In addition, Voyager 2 uncovered a profound secret beneath the icy exterior of Europa, one of Jupiter's 53 named moons. Its icy shell, it revealed, was a staggering 60 miles thick, prompting scientists to reconsider their understanding of these distant celestial bodies. This revelation fueled a growing curiosity about the potential habitability of icy moons and the potential for extraterrestrial life. As the Voyagers bid farewell to Jupiter, they received a crucial gravitational boost, like a cosmic slingshot, which propelled them toward their next destination, Saturn. Without this parting gift from the gas giant, they would have remained trapped in the gravitational clutches of the sun, unable to venture deeper into space. With a sense of wanderlust, Voyager 1 altered its trajectory, approaching Saturn's mysterious moon, Titan, cloaked in a strange orange haze. This enigmatic moon held the promise of profound discoveries, inspiring extensive research into its complex chemistry. Voyager 1 then turned its course northward, departing from the plane of the planets and commencing its journey into the uncharted territory of our solar system's outer fringes. Meanwhile, Voyager 2 embarked on a series of celestial adventures that would lead it to the outermost planets of our solar system. In 1986, Voyager 2 etched its name into the annals of space exploration with a historic flyby of Uranus. This mission was no ordinary visit. Voyager 2 gifted humanity with the discovery of 10 previously unknown moons, thus enriching Uranus's lunar population. This distant ice giant had a few more companions than we had previously thought. 3 years later, Voyager 2 continued its cosmic pilgrimage, reaching Neptune, the inscrutable cobalt-blue world nestled in the outer reaches of our solar system. The encounter with Neptune was nothing short of astonishing. The spacecraft recorded wind speeds clocking in at a jaw-dropping 1,000 miles per hour, marking a record for the fastest winds ever documented on a planet within our cosmic neighborhood. As Voyager 2 ventured within a mere 2,980 miles of Neptune's ethereal, methane-rich atmosphere, it unveiled unprecedented insights into this distant realm. The ice giant's largest moon, Triton, emerged as one of the most frigid locales in our solar system, with surface temperatures plunging to an astonishing -391 degrees Fahrenheit. Triton wasn't just a deep freeze, it was a world of wonders. It flaunted its unique traits, including ice volcanoes that spewed nitrogen gas and icy particles, shooting them 5 miles high into its thin, misty atmosphere. These groundbreaking revelations expanded our comprehension of the diverse and intricate celestial bodies lurking even in the remote domains of our solar system. Amidst these celestial revelations, one individual played a pivotal role in the mission's extension beyond its original objectives. The renowned astronomer Carl Sagan was a steadfast member of the Voyager mission's imaging team. Driven by an unrelenting passion, he fervently advocated for capturing one last set of images before the cameras on both spacecraft were powered down. Sagan's tenacity prevailed. These images, known as the pale blue dot photographs, would serve as a poignant parting gift to humanity. They offered a final, humbling glimpse of our home planet from the far-flung realms of interstellar space, underscoring the fragility and magnificence of our pale blue dot in the cosmic sea. On a romantic note, on Valentine's Day in 1990, Voyager 1 did something heartwarming. It turned its camera back toward the heart of the solar system and snapped a series of 60 images. Among them, one image stands out as the stuff of cosmic legend: the pale blue dot. Captured at an astonishing distance of 3.8 billion miles, it's the farthest snapshot of our beloved planet in history. This iconic image portrays Earth as a minuscule, pale blue pixel, barely perceptible in the vast fabric of space. It's a powerful reminder of our humble place in the grand cosmic scheme, evoking both wonder and introspection. The Voyager missions read like a tale of space-age superheroes. Their durability and longevity are the stuff of legend. Even after 4 decades of venturing through the cosmic expanse, they're still out there, serving as cosmic emissaries, relaying invaluable data from the farthest edges of our celestial neighborhood. Management of Voyager Twin Probes components. In the ever-expanding void of space, Voyager 1, now a staggering 14.5 billion miles from Earth, has unveiled a recent and remarkable revelation: the detection of 500 unidentified objects as it journeys through the cosmos. These enigmatic entities are entirely new to our understanding, defying our preconceived expectations of the celestial realm. This unexpected discovery prompts us to ponder the possible explanation behind this cosmic enigma. Could it be attributed to the aging components of the spacecraft itself? Voyager 1, after all, embarked on its epic odyssey in 1977, making its electronic systems over 45 years old. In usual circumstances, one might anticipate signs of wear and tear or even a systems failure in hardware of such vintage. However, Voyager 1 defies these expectations, standing as proof of remarkable resilience. One key to its endurance lies in the redundancy of its computer systems. Voyager 1 boasts dual redundant computer components, essentially having 2 sets of hardware. This ingenious redundancy ensures the spacecraft can seamlessly switch between systems as needed, extending its lifespan and preserving the efficiency of Voyager 1's computer systems. Engineers have worked tirelessly to employ various strategies to conserve and optimize power. The spacecraft relies on radioisotope thermoelectric generators, RTGs, to maintain its essential energy resources. These power sources are the lifeblood of the Voyager missions, converting the heat produced by the gradual decay of plutonium into vital electricity and keeping the spacecraft running smoothly. Voyager 1 and its sibling, Voyager 2, utilize simplified systems with hardwired logic for their instruments, and they feature a remarkable 6 onboard computers operating within a distributed system. This redundant approach to computing allows them to withstand the relentless test of time in the harsh cosmic environment. It's important to note that these nuclear power sources gradually lose approximately 4 watts of energy each year, a consequence of the slow decay of the plutonium they rely on. However, the remarkable feat of engineering that keeps these spacecraft operational thrives on this very process. The natural decay of plutonium produces heat, which is masterfully harnessed to generate electricity, thus perpetuating the Voyager's missions. An intriguing facet of managing power in this cosmic ballet involves selectively turning off non-essential systems. Engineers meticulously identify and power down specific components or subsystems that aren't crucial to the primary mission objectives. For instance, in the unforgiving chill of outer space, the Voyager probes have had to adapt in ingenious ways to ensure their survival. These spacecraft were originally equipped with heaters designed to maintain specific instrument temperatures for optimal performance. However, in the interest of conserving power and extending their already impressive lifespan, engineers made the deliberate decision to deactivate these heaters. The results were twofold: less power usage and the extension of the probe's operational capabilities. Yet maintaining a delicate balance is key to managing the spacecraft. In the frigid vacuum of space, where temperatures can plummet to extremes, there's a necessity to prevent certain vital lines from freezing. Typically, they are kept around 2 degrees above absolute zero. If these lines were to freeze, the spacecraft might lose its ability to accurately point toward Earth, a scenario that could jeopardize communication. Voyager 2, as an added safety measure, is equipped with a backup power source that can sustain one more scientific instrument until 2026. This redundancy provides an extra layer of assurance as power gradually dwindles on these venerable explorers. However, the diminishing power reserves are felt across various systems, not only in the scientific instruments. The spacecraft's heating mechanism, which consumes significant energy, may require the deactivation of more heaters to ensure that the remaining instruments continue to function optimally. These probes are equipped with small thrusters vital to their operation. These thrusters are responsible for maintaining the spacecraft's orientation, ensuring that their antennas remain precisely aligned with Earth for data transmission. The spacecraft carries a finite tank of fuel for these thrusters, which are used in short, controlled bursts. If these fuel lines were to freeze, engineers would lose the ability to steer the spacecraft, potentially rendering them inoperative. In addition, these thrusters, over time, may experience wear and, at times, mechanical breakdowns. An illustrative instance comes from 2017, when some of Voyager 1's thrusters had to work harder to maintain their orientation toward Earth. In response, engineers activated secondary thrusters that had been dormant for an astonishing 37 years. The reliable primary thrusters on Voyager 2 have been loyal workhorses for decades, but time has taken its toll, showing signs of wear. In a strategic move to ensure continued control, engineers have planned to call upon the backup thrusters on Voyager 2. While these backup thrusters haven't been inactive for as long as Voyager 1's, they've had their fair share of dormancy and slumbering since Voyager 1's encounter with Neptune in 1989. That's nearly 30 years of rest for these silent heroes. NASA, the venerable custodian of these interstellar adventurers, is optimistic about the prospects of several more years of operational capability in these remarkable spacecraft. Their continued service is vital because the Voyager probes are not just relics of the past, they're beacons of cosmic insight in the present. The region of space they currently explore is teeming with mysteries yet to be unraveled. The eventual day when the Voyagers are powered down may be on the distant horizon, but it's a decision made with utmost care and precision. It involves a meticulous evaluation of the trade-offs between saving power and achieving the mission's scientific goals. Engineers and scientists collaborate closely, weighing the impact of turning off specific systems on the quality and availability of the scientific data. The ultimate aim is to strike a harmonious balance that conserves power while ensuring essential functions run smoothly, gathering valuable cosmic information. Adaptive power management strategies come into play, responding to the ever-changing environmental conditions. As Voyager 1 voyages farther from the Sun, it's bathed in less solar energy. To make the most of its dwindling resources, the spacecraft shrewdly adjusts how it allocates power because every electron counts as these explorers venture deeper into the cosmic unknown. Throughout the years, the Voyager mission has seen notable strides in power management, bolstering the probe's power systems. These enhancements span a range of technical improvements, such as optimizing power distribution, refining battery charging techniques, and making significant advancements in power regulation and control. These meticulous power management strategies serve as the unsung heroes, effectively extending Voyager 1's operational life. This means the spacecraft can keep charting the cosmic realms and beaming back essential data. Remarkably, though the mission's original blueprint only projected 5 years of exploration, the unwavering dedication of scientists and engineers has defied the odds. They've sustained the Voyager mission, propelling it through the depths of space. Now it's time for today's subscriber pick. The world held its breath as the headlines blazed with excitement. Voyager 1 has made impossible discovery after 45 years in space. For decades, the aging spacecraft had ventured beyond our solar system, sending back faint whispers of the cosmos. But now it had uncovered something that defied every law of physics known to humanity. The year was 2068, and Voyager 1's instruments recorded a strange symphony of sounds echoing through the interstellar void. These ethereal notes, seemingly composed by the universe itself, left scientists baffled. Their spectrographs revealed a harmonic pattern that should have been impossible, a celestial riddle that hinted at an undiscovered dimension of reality. As the world's best minds grappled with this mystery, a brilliant physicist, Dr. Elena Quinn, emerged as the forefront explorer. She theorized that the harmonious wavelengths might offer a wormhole, a passage to an uncharted realm of existence. Her bold hypothesis captured the world's imagination, and her team tirelessly worked to decipher the cosmic melody. Months of calculations and experiments followed, and the world held its breath once more when Dr. Quinn's team successfully opened a microscopic portal. On the other side, they glimpsed a realm of shimmering colors and geometry that transcended human comprehension. It was a threshold to the unimaginable. Voyager 1 had become humanity's key to unlocking the mysteries of a multiverse, and the journey had just begun. As the news spread across the globe, the world dared to dream, to imagine the unimaginable, and to reach for the stars with a newfound hope. For Voyager 1 had turned science fiction into reality. What do you think? Let us know in the comments below. Voyager's interstellar journey. Both Voyager missions have ventured so far from Earth that a radio signal traveling at the speed of light requires almost 22 hours to reach Voyager 1 and slightly over 18 hours to reach Voyager 2. These intrepid spacecraft progress by 3 to 4 light seconds every day. The NASA Deep Space Network, a trio of tracking facilities scattered across the globe, serves as their lifeline, enabling uninterrupted communication with the probes as Earth rotates. As the Voyagers journey through the vastness of space and time, their signals grow fainter, drowned out by the cacophony of terrestrial noise radios, televisions, cell phones, and more. Even though these signals are faint, they have already defied astronomers' expectations, reshaping our understanding of their interstellar odyssey. It's important to distinguish the boundary of the solar system from true interstellar space. Similarly, the Oort cloud, a distant assemblage of comet-like objects held together by the sun's gravitational pull, may extend halfway to the nearest star. However, it will take the Voyagers at least another 300 years to reach its outer fringes. In contrast, interstellar space, where the solar wind ceases, is far more accessible. The solar wind is a ceaseless torrent of charged particles and magnetic fields emitted by the sun and other stars, racing through space at hypersonic speeds. Imagine the sun as a gigantic balloon, constantly exhaling a stream of charged particles and magnetic fields. This is the solar wind. This cosmic breath inflates what astronomers call the heliosphere, a protective bubble around our solar system. As it expands, it carries the sun's magnetic fingerprint into space. But as this solar breath pushes further, it encounters resistance from interstellar matter, like a gentle breeze slowing against a solid object. This boundary, where the solar wind meets interstellar space, creates a colossal shock wave known as the termination shock. It's the outer sentinel of our cosmic neighborhood, discovery of unexpected observations of heliopause. As the Voyager probes embarked on their incredible interstellar journey, they encountered a significant milestone: the heliopause. This boundary acts as the cosmic divide, separating our sun's dominion from the vast reaches of interstellar space. Intriguingly, the heliopause's precise location long eluded scientists, giving rise to a fabric of estimates and theories. Early predictions positioned it as close as Jupiter, but later, refined calculations offered a more accurate understanding. In 1993, the skilled astronomer Bill Gurney projected the heliopause to lie between 116 and 177 astronomical units, AU. To grasp the enormity of this scale, remember that 1 AU is roughly 93 million miles, the expanse between our Earth and the Sun. Remarkably, Gurney's estimations proved to be incredibly precise. Almost 2 decades later, Voyager 1 reached the heliopause, unveiling the expected increase in plasma density. Yet this milestone also posed a perplexing riddle. Voyager 1, while at the heliopause, detected a surge in plasma density but did not encounter the anticipated shift in the ambient magnetic field direction. This was surprising because if the spacecraft had transitioned from a realm where the magnetic field was sun-originating to one sourced from other stars, a noticeable alteration should have manifested. The mystery of this unanticipated consistency in magnetic fields would continue to intrigue scientists on Earth, emphasizing the complexity of the cosmos and the mysteries that Voyager 1 was unraveling. Voyager 2, the companion to its twin Voyager 1, deepened the enigma when it reached the heliopause at precisely the same distance, 120 astronomical units from Earth. However, just like its predecessor, it also failed to detect any magnetic field changes at this cosmic boundary. The baffling consistency in their observations sent shockwaves through the realm of theoretical models that aimed to understand the dynamics of the heliosphere and its interactions with the interstellar realm. The scientists' forecasts anticipated that the heliosphere's behavior would sync with the Sun's 11-year cycle. But the data from the Voyagers didn't align with this expectation. Adding to the intrigue, the solar wind, which typically waxes and wanes in tune with the Sun's cycle, was at its most potent when Voyager 2 reached the heliopause. These unexpected findings challenge the notion that the heliopause should have been positioned farther out, extending beyond the 120 AU mark, further complicating our understanding of this cosmic border and the celestial forces governing it. The Voyager's data has proven invaluable in honing our understanding of the cosmos. Scientists now propose that our Sun has evolved from a scorching, ionized domain to a partly ionized expanse within our galaxy. This transformation likely sprang from the explosions of nearby supernovae, ancient stars that, upon their final fiery breath, not only heated the surrounding cosmic neighborhood, but also stripped electrons from neighboring atoms. Think of the boundary between these two realms as a cosmic shoreline, where turbulent waves of change mix magnetic fields in a complex dance. While the level of turbulence can ebb and flow, the Voyager's vigilant observations have shown minor fluctuations near the heliopause, while revealing larger-scale alterations are negligible. As these ageless wanderers, Voyager 1 and Voyager 2, continue their solitary sojourn through interstellar space, they leave behind the planets and moons that were once their companions. But what awaits these indefatigable travelers beyond the cosmic horizon? The fate of these intrepid probes is similar to a celestial riddle, and several intriguing possibilities loom. Voyager 1 races toward the constellation Ophiuchus, while Voyager 2 charts a course for the constellation Cetus. Some have prophesied their cosmic demise around 2030, but the story is far from over. These indomitable spacecraft may well outlive our species, enduring for countless millennia. Voyager's twin probes bid farewell. Anticipations run high as these venerable spacecraft approach a pivotal juncture in their journey. The turbulent shoals of the outer solar system will soon give way to the pristine expanse of the pure interstellar magnetic field. Yet bidding adieu to these trailblazing Voyagers will be an emotional undertaking, for the end of any long, remarkable voyage is always tinged with a sense of loss. Currently, Voyager 2 houses 5 operational instruments, while Voyager 1 carries 4. Their tenacious endurance stems from a unique power source, a mechanism that converts the heat generated by plutonium's radioactive decay into electricity. But even this energy source wanes, decreasing by approximately 4 watts each year. Yet their odyssey continues. Voyager 1 will venture past Proxima Centauri, our closest neighboring star, in a staggering 16,700 years. Voyager 2 follows suit, though it will take an additional 3,600 years. These stalwart travelers will continue to orbit the galaxy for millions of years, far beyond our sun's demise and the vanishing of the heliosphere. Even in silence, they may bear a final message. 2 antique technology artifacts, copper records with a golden veneer encased in aluminium, capture images and sounds, weaving a fabric of Earth's essence. They house 90 minutes of music, from Bach's Brandenburg Concerto No. 2 to Chuck Berry's Johnny B. Good, and depict moments like the laughter of children, the dance of dolphins, the serenity of sunsets, and the chorus of crickets on a warm evening. These recordings encapsulate our humanity, etching our story into the cosmos. In the spirit of unity, Jimmy Carter, the President of the United States during their launch, contributed a message. "We cast this message into the cosmos," it reads. "We hope someday, having solved the problems we face, to join a community of galactic civilizations." This record represents our hope, determination, and goodwill in a vast and awesome universe. The Voyagers, silent ambassadors of Earth, continue to navigate the boundless sea of interstellar space, carrying with them the echoes of our existence and the hopes for a cosmic connection yet to be made. Thanks for watching, and we'll see you in the next one.